Alright, so here we are, Project Euler number 10. It's a surprisingly straightforward question for once. It just says the sum of primes below 10 is 2 plus 3 plus 5 plus 7, which is 17. I agree with that. And then the question is just find the sum of all the primes below 2 million. So I think the key thing here is that we know how to sum a list of numbers. That's fairly straightforward. What we don't know is how to get a list of prime numbers. So let's work that out. And rather than getting a list of prime numbers, let's try and get something called a lazy list of prime numbers. And the reason for that is that we're not going to want to necessarily compute all prime numbers, but we want to have the option to compute as many as we like. And the way that lazy lists work in Scala is that they will compute only the elements that you need and nothing more. It's really cool and like some sort of dark magic. The syntax is a bit weird though. I think it's this sort of mysterious um, hash colon colon or something like that. Um, mm, let's see. Let's see. And then I believe it has a from method. So we're going to want to start from 3. So we know that the first prime number is 2. We know the next prime number is 3. And then we want to filter the rest of the list such that we're only keeping prime numbers. But how do we know if something's prime? Well, we need to define a function called isPrime that's going to take an integer and tell us if it's prime or not. And I'm not really sure how we're going to do that yet. If only we had a list of prime numbers so that we could check if the number that we're interested in doesn't have any of the already existing prime numbers as factors. If only we could do that, eh? If only. So, what we can do is use the primes that we already have to figure out if n is prime. And the way that we can express this is we want to say that for all of the primes that we've already found, and let's call one of those primes just p, we want it to be the case that they're not a factor of n, and the way to express this in Scala is to have a look at the remainder when we divide n by p, and we just have to say that that's non-zero. So in other words, for all of the primes that we found, none of them are factors of n. That's what that's saying there. Now, there's a problem with this. I think I said at the start, this is an infinite list, and I'm saying a for all on an infinite list. So I think if I was to try and do something fairly straightforward, like take the first 7 of these and print them out, I think what's going to happen is we're going to get some sort of horrendous Stack Overflow error or something like that. So let's double check, because to be honest, like, my recursion isn't great. So let's see. So it says a self-referential lazy list or a derivation thereof has no more elements, which is kind of a different error message to what I was expecting, actually. Interesting. Where are we getting this error message? Well, let's see where it comes from. So we can see that this is where the exception is getting thrown, and it's giving us a bit more information in the comment. So if it's already mid-evaluation, we're stuck in an infinite self-referential loop. Also, it's empty, it being the list. So I think we can understand what's going on by thinking about what this function's getting called with, I suppose. So we're printing 2, which is all well and good, because I've literally put 2 as the sort of first element of the list. And then for the rest of the list, that's when it tries to compute the rest of the list, that's why that exception gets thrown. So it's because when we're trying to process element number 3, when we're testing that with our filter, when we're testing if 3 is prime, when we're going through all of the primes, what's happening is it's got to a point in the list where we've not computed anything yet, but we're already trying to compute it. so that's why we get an error message. So we're going to need something sort of here. Star slash, is that the syntax? Yeah. So we're going to need something sort of here to make sure that the list of primes that we're looking at are ones that we definitely have already computed. Yeah, so let's go ahead and do that. Alright, so we need to make sure that we're only taking a sort of subset of the primes when we're deciding which ones we need to use to determine if n is prime. Again, by checking are the primes that already exist factors of n or not. That's what the for all does, but we also need to choose which primes we need to judge. So I think the naive approach would be to just check all primes that are less than n. There are two reasons this is bad. So one is that it's not the most efficient way of doing it in general, and the other one is that we'll get the exact same error message if we run this, because what's going to happen is when we get to this take while part, it's going to be like, okay, let's take everything that's less than 3, so it's going to take 2 for sure, and then it's going to try and decide if it needs to take the next element. Except the next element hasn't been computed, as we already know. So if I run this, it ain't going to work, and it's going to give us the same error message. Great. And also, I'm not sure why IntelliJ was underlining Latin res. That was really weird. So, if we can't use that naive condition, let's work out what condition we should use instead. So we can do this with an example, and I think I might have explained this before, but I can't quite remember. So we'll think about a number that we want to test for primality. So it might be something like 144, and we can start just writing out the factors of it, which I'm definitely not reading off a different screen. I'm definitely working all of these out in my head as I am typing out. I don't know why I didn't just copy and paste this, sorry. So 144 has these guys as its factors. It's 2 times 72, 3 times 48, 4 times 36, 6 times 24, 9 times 16, and 12 times 12. So if we want to test it for primality, we only actually care about these ones, because let's say for as an example, 9 and 16 are both factors. So once we've reached the check for 9, that's it. We don't need to go any further. So we never need to check this factor, or 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 this factor. Therefore, we only actually need to check factors up to the square root, and including the square root of 24. Sorry, the square root of 144, which is 12. So we can essentially do that and change our condition to be p is less than or equal to the square root of n. So if I run the program, I am hoping that it'll actually print out the first 7 primes for us. So let's see. Fantastic, there we go. And I might just rewrite this, effectively squaring both sides of that expression, just so that we're always dealing with integers, as I think that's slightly nicer. So let's just check that works again. Stunning, look at that. Okay, so now we have to remember what on earth this problem was. So you can see I was sort of looking at streams. I'm going to talk about this at the end later. But the problem was the sum of all primes below 2 million. So we have a way of getting primes. We have a way of getting primes that are below 2 million. So 2 million is that. So take while 2 million. It's not going to work, is it? So was it strictly less than or below 2 million, say strictly less than, and we want to sum them. And I think my sort of special timer is clever enough to be printing out the result, is it? Yes, okay. So let's see if this works. I suspect we might get an integer overflow actually. Okay, maybe not. So that might have an integer overflow in it, I don't know. Let's check it. 2, 6, 3, 8, 9. Yeah, it's probably an integer overflow. So if we do this, just because like the sum of these guys is going to be pretty enormous. We need to make sure we don't get into overflows. To be honest, probably a long would do it actually, rather than using a fully fledged big int. So that number's clearly different than before, and it looks like it's a long. It looks like a long would be sufficient. But you know, whatever. 007, nice. Yes, that's the correct answer. Excellent. Alright. The answer, but there's still a bit more to talk about. So one is this that you know is basically the same as what I've done, and to be honest, I think when I first did this problem, this is probably where I got the answer from. Stream, I think, is a thing that's in like Scala, earlier versions of Scala. Lazy list is what we use these days. And interestingly, the best answer, and this is better than my entire video, to be honest. And I should have read it before making the video, but I didn't. It explains everything that I've explained, but more concisely and better, including the stuff about why using that naive constraint doesn't work, and also why we can get away with the sort of this bit here, where you're only looking for ones where the prime number is less than the square root of the number that you're testing for primality. And I think the other thing I wanted to highlight was that you can read about the lazy list documentation in general as well, which is really nice. And it has an example that's pretty similar to what we've been doing actually, which is the Fibonacci numbers instead of prime numbers, but it's similar in the sense that it's something that's defined in terms of itself. So yeah, I'd say this is worth a read as well, and I'll be popping this in the video description as well. Anyway, thanks for watching, hopefully it wasn't too painful, and I will see you next time. Goodbye.